Welcome to AP Chemistry at Heineck High School. I'm Brian Brown, and today we'll be looking at the first couple of sections of Chapter 20, our chapter dealing with electrochemistry. Now, like many of the chapters, well, all of the chapters that we've looked at in second semester, this is a major area of emphasis on the AP test. This is one of the big five, along with equilibrium, kinetics, acid-base chemistry, and so on. So on the multiple choice section, you're going to typically see about 5 questions out of the 75 questions dealing with concepts related to electrochemistry. And we touched on a little bit of electrochemistry back on chapter 4. So a few of these ideas are going to be a repeat of stuff we looked at earlier. And typically somewhere in the FRQs, there's going to be almost every single year a question related to electrochemistry. So we finish up our chapters on chemistry dealing with something that's very important for you to understand for the AP chemistry test. The first section gets into oxidation states and oxidation reduction reactions, something that I actually introduced back in chapter 4. So a lot of what we're going to look at today is really re-emphasizing and reviewing things we looked at earlier, and then we're going to add one new thing to the end. Now, in electrochemical reactions, electrons are transferred from one species to another. So the types of reactions we're going to look at in chapter 20 all involve transfers of electrons occurring between the species and the reactions. Now these types of reactions, like I said, were discussed back in chapter 4, and back then we called them oxidation reduction or redox reactions for short. Now, in order to understand what is being oxidized, what's being reduced in our transfer of electrons between species that's occurring, something that helps us track electrons is oxidation numbers. So in order to keep track of what loses and what gains these electrons, we assign what are called oxidation numbers. Oxidation numbers is like the assumed charge of a substance. And there are some rules we use in assigning these oxidation numbers. And a couple of them you can see in the example over here. It looks like when we have a monatomic ion, the oxidation number is the same thing as the charge. Remember, that's what oxidation number is dealing with, is assigned charge. So in these two cases, since we know the charge on those monatomic ions, we know the oxidation numbers. Now, hydrogen gas and zinc solid, those are both elemental substances in their elemental state, and those both ended up as zeros. So that's also going to be one of our rules of oxidation numbers. So our basic rules here. One, elements in their elemental form have an oxidation number of 0. We just looked at that. The oxidation number of a monatomic ion is the same as the charge. We also looked at that. So those are fairly straightforward. If you got an element in its elemental form, you're going to have a 0 as an oxidation number. And if you have an ion, the charge of that ion is the same thing as its oxidation number for a monatomic ion. Now, rule 3 gets into where we have to start remembering things and applying. Nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds. So nonmetals are things that tend to grab electrons, so they're going to have a negative charge as they pick up electrons. Good example of that, a very, very common nonmetal is oxygen. Oxygen has an oxidation number of -2, and that's what it is in almost every single case that we look at. But there is a very common substance, hydrogen peroxide. It's not an oxide, it's a peroxide. Well, peroxides are oxygens with an oxidation number of -1. Very, very, very rare, except for this. Watch out for hydrogen peroxide. So typically, if we see oxygen, we're going to know we're going to have an oxidation number of -2. That's one of the important ones to remember. Another important one, another common element would be hydrogen. Hydrogen is a -1 when it's with a metal, and a +1 when it's with a nonmetal. Third idea here related to nonmetals, fluorine is always -1. Its oxidation never varies. Now the other halogens can be -1, but there are also many other numbers besides that. Fluorine never varies, it's always a -1. But it's a fairly rare substance, and we don't see it all that often. So this is not as really as important. It is true, if you see fluorine, it's going to be a -1, but we can often figure that out by other evidence, which where rules 4 and 5 come in. The big things to remember, oxygen -2, hydrogen is a positive when it's with a metal, +1, and negative when it's with other nonmetals. And that brings us to rules 4 and 5, how we figure everything else out once we remember what oxygen and hydrogen are. Well, you need to know that the sum of the oxidation numbers in a neutral compound is 0. So neutral, charge is 0, oxidation numbers have to add up to 0, which means if we have a polyatomic ion, the same idea applies. So there's not much difference between rule 4 and rule 5 here. If you have a polyatomic ion, the oxidation numbers have to sum up to the charge of the polyatomic ion. So remember, all of your oxidation numbers add up to the overall charge. So let's practice a couple of these and try it. So what would be the oxidation numbers for the substances in SO2 and NaH and so on? So in SO2, sulfur dioxide, what's the oxidation number for the sulfur and what's the oxidation number for the oxygen? Remember, the rule we looked at was oxygen's always -2. So it's not a peroxide. It's not that rare exception. So we know that the oxygen is -2. Well, then our total for the oxygens would be a -4. So two negative 2's is a -4. So we know we have a total here of -4. Now, remember the total charge has to, or all the oxidation numbers have to add up to the total charge. Well, SO2 has no charge. So if the oxygens add up to -4, that means the sulfur has to add up to a +4. So we know that the sulfur is going to be a 4. So in SO2, sulfur has an oxidation number of 4, oxygen has an oxidation number of -2. Now, got a couple more here that I want you to try. So at this point, stop the tape and practice this yourself. Make sure you get this idea. So you're not just copying down what I say. Make sure you try it at this point. So stop the tape here. I'm going to wait for you. Make sure you stop the tape and try NaH and CaNO2. Okay, sodium hydride. First one we're going to look at here, and hopefully you did this right. Remember, oxygen's always -2. Well, we don't have an oxygen here. Hydrogen with a metal, we're supposed to know that's a +1 with metals and a -1 with other nonmetals. Oops, I said that exactly wrong. Hydrogen is a +1 when it's with other nonmetals and a -1 when it's with metals. So if hydrogen's got to be a -1, and the total charge is 0, that means sodium has to be a +1. So hopefully this one didn't take you all that long. So hydrogen with a metal here got to be a -1. There's only one other species, got to add up to 0, so that's a 1. Now it gets a little more complicated when we look at copper and the NO2, which is nitrite. So this is actually, I'm sorry, calcium with nitrite. So this is the compound calcium nitrate. Now you may remember nitrite, which is NO2, has a charge of -1, and there's two of them. Well, that must mean our calcium must be a +2 here. So that one I can see right away. Well, how do I figure out our N's and our O's? Well, honestly, I'm not really going to look at the calcium nitrate. It's easier for me to analyze what's going on with NO2 minus here. So when you take a look at what's happening, remember NO2 is nitrite and it's a -1. There's two of them. That must mean the calcium's got to be a +2. So we can figure that one out. Now to figure out our N and O, don't look at this substance. Really concentrate on the NO2 minus down here at the bottom, because we know oxygen is a -2, and we know we've got two oxygens, so that's -4. And in this case, it's got a charge of -1, so we know it has to add up to -1. So what plus -4 equals -1? Got to be a 3. So we know nitrogen is a +3 and oxygen is a -2. Now, you got to get good at this because it's when we go to do redox reactions, we have to find out what's oxidized, what's reduced. First step in that process is assigning our oxidation numbers, because it's much easier to track electrons by looking at how oxidation numbers change than it is by looking at anything else. Now there's a short movie on redox that we'll be looking at in class, or you can go online and watch it. So let's say we've got a redox reaction. In this reaction somewhere we've got a transfer of electrons. Where are electrons being transferred and how are those things happening? Well, the first thing we want to do is assign our oxidation numbers. Remember, a species is oxidized when it loses electrons. That's the definition of oxidation from the book. So in oxidation, what's happening is the oxidation number is going to increase. That's why we call it oxidation. Oxidation number is going up. So if you look at our oxidation numbers in the reaction above, notice zinc is going from a 0 to a +2. That means zinc is involved in our oxidation. So Zn to Zn2 plus is our oxidation reaction. Now how can Zn magically become 2 plus? Well, only if it loses a couple of electrons. So oxidation, which is when we increase the oxidation number, also involves a loss of electrons. Now a species is reduced when it gains electrons. So in reduction, what's going to happen when we gain electrons is our oxidation numbers are going to go down. That's why it's called reduction. In oxidation, our oxidation number is going up. In reduction, our oxidation number is being reduced, hence the name reduction. So reduction, the oxidation number is going to go down. So in the reaction up above, H plus was a +1, and it went to hydrogen gas, which is a 0. So that's going down. That's our reduction reaction. So we have, if we balance it here, 2H plus is going to H2. Once again, how can that magically happen? Well, only if we add some electrons. And that's why reduction is a gain in electrons. One way to remember oxidation is losing electrons, reduction is gaining electrons, is to remember the acronym OIL RIG. So oxidation is a loss of electrons. Reduction is a gain of electrons. There's another one that is Leo the lion goes grr. Not everybody may remember that whole statement, so I think oil rig is a little bit more straightforward, but loss of electrons, oxidation, gain of electrons, reduction. So another way to an acronym for this that you'll sometimes see in books or people use is Leo the lion goes grr. So in the case of our reaction, we can look at oxidation numbers to figure out what's being oxidized or reduced, or we can track electrons. Now another new bit of terminology that we're going to use here is what is reduced in a reaction. And remember, we established a second ago that hydrogen H plus going to hydrogen gas was what was reduced. Well, what is reduced is called the oxidizing agent or the oxidant. And that's because whatever is reduced is causing the oxidation. Oxidation and reduction have to happen hand in hand. You can't have one without the other. So if we have oxidation, we can't have that oxidation unless we also have reduction. Something needs to provide our electrons by losing them, and something else needs to gain our electrons. So those two things work hand in hand. So what is reduced is actually known as the oxidizing agent because when it gets reduced, it causes the oxidation. So H plus was oxidizing Zn by taking electrons from it. So H plus, which was our species that was reduced, is also our oxidizing agent. What's oxidized is what's known as the reducing agent or reductant. So in this particular case, Zn reduces H plus by giving it electrons. And so therefore Zn, which is what's oxidized, is known as the reducing agent. Another short movie we're going to watch in class here. Now, second thing that we get into is the next section, 20.2, which is balancing redox reactions. And I prefer to use the half-reaction method, which is the same method most textbooks use, because I think it's one of the easiest ways to balance redox reactions. And this is something we did back in first semester. So I'm going to go through this fairly quick at the beginning because this is all a repeat of something we've done before. Now, what we're doing in the half-reaction method is we're going to treat on paper our overall reaction as two partial reactions. We're going to break it into our oxidation and reduction processes. So we're going to take a whole reaction and break it into halves, hence the half reaction method. And then we're going to balance each individual half reaction because honestly, it's easier to balance them alone than to balance them when they're mixed up. And then we're going to combine them together to get an overall balanced equation. Now, rules for this. One, we assign oxidation numbers to determine what's oxidized and what's reduced. How do we break into our oxidation and reduction reactions if we don't know which is which? Two, we're going to then split and write our oxidation and reduction half reactions. So we're going to take the overall reaction, assign oxidation numbers, and then use that to split it into our half reactions. Now, next comes the important thing. We're going to balance each individual half reaction. First, we're going to balance the elements, not hydrogen and oxygen, just like we always do by adding coefficients. So you don't balance your H's and O's. You balance everything but that, just like traditional balancing. Now, second, we're going to balance our oxygens by adding water. If we've got oxygens on one side, we're going to add water to the other. If we had 6 O's on the left, then we got to add 6 waters on the right. Now, since that changes the number of hydrogens, we wait on balancing our hydrogens until after we balance our oxygens, and then we're going to balance our hydrogens by adding H+. Now, technically what we're doing is we're balancing this reaction in an acidic environment because that's what H+ is our acid ion, hydronium. So if we're going to balance in a basic reaction, we're going to do all this, but we're going to do a slight twist at the end. And that's really the only thing that's new because everything here we've talked about. D is the trickiest step. This is where you got to watch out for. Balance your charge by adding electrons. So pay close attention when we look at the sample for this. Now, once we've done this for both reactions, now we need to balance our electron transfer. One reaction is providing electrons. The other reaction needs electrons. Well, they have to provide and need at the same rate. And when we balance our half reactions, our number of electrons involved may not be equal to each other. So we multiply the half reactions by the smallest common or number to get the electron transfer to be equal. Once again, pay close attention. It's not that bad when you see it done. And then in step 5, we're going to add the half reactions together and subtract anything that appears on both sides and cancel to get our overall balanced reaction. Now, at this point, you're technically done for balancing a redox reaction in an acidic environment. But don't skip steps 6 and 7 because they only take a few seconds. And since this is a fairly tedious process, it's sometimes easy to make mistakes. You can easily catch those mistakes if you do step 6 and 7. First, make sure your reaction is balanced according to mass. That means count the atoms. Remember, you have to have the same number and type of each atoms at the beginning. So the stuff on the left have to equal the stuff on the right. The second thing is what you don't normally do, and that's balance by charge. If it started out as an overall charge of 0, it's got to end at an overall charge of 0 if your electron transfers were really balanced. If it started out as an overall charge of -2 on the reactant side, then on the product side we have to have a -2. Or I can't remember, did I say +2 or -2? So whatever the charge is on the left total has to equal the charge on the right. If it doesn't, you made a mistake. Go back and look at your step 4 more closely. You probably messed up on the electron transfer. So let's try it. Consider the reaction between MnO4 and Fe2+. This is a reaction we did earlier in the year in a lab. So what you'll often see is, we've got permanganate, MnO4 minus, and it is reacting with Fe2+ to make Mn2+ and Fe3+. Well, the first thing we need to do is establish what our two half reactions are, and that means assign oxidation numbers. Now, Mn, in this particular case, is going to be a +7. The reason we get that, remember our process. We know O is always -2. We've got 4 of them. That's -8. What plus -8 equals -1? +7. So go through and do that with each of our species. All the rest are monatomic ions, so they're nice and easy. And once you see what's going up or down in oxidation number, you know what's being oxidized and what's being reduced. So the manganese in MnO4 is being reduced, and the iron is being oxidized. Now I can split into those two half reactions. So Fe2+ becoming Fe3+, that's our oxidation half reaction. Now you go through steps 3. I put them up here to make it easier. Balance the non-O's and H's, that's done. 1 to 1. And I don't have any O's and H's, so B and C are also done. And that brings us to E. I'm sorry, that brings us to part D of this. Balance the charge by adding electrons. Here's where you got to be careful. Since everything is already balanced by electrons, you've got to evaluate charge to see what's happening with electrons. This side has a total charge of +2. This side has a total charge of +3. Now, if it's balanced, the charges are going to equal each other, and they're not. So there must be something missing. Well, what's missing? Electrons are what's missing. Now, since electrons are negatively charged, the secret is you add the difference between the two charges to the side that's more positive. So this side is more positive by 1. So that means we're going to add 1 electron to the right. So that's really all you're doing in balancing charge, is you're adding the number of electrons to the more positive side to get them to equal each other. Now I've got a +2 on the left and 3 plus -1, +2 on the right. It's balanced by charge. Now we turn around and do the same thing for the other reaction, MnO4 minus becoming Mn2+. Now, in this particular case, this is our reduction reaction. But if you follow through, MNs are balanced, so part A is done. Part B, balance our O's. Well, we got 4 O's on the left, but none on the right, so we're going to add 4 waters to the right. That takes care of the oxygens. And now since we've added hydrogens, we now have to balance our hydrogens by adding H+. So in this particular case, we have to add 8 H pluses to the left because adding 4 waters gave us 8 hydrogens on the right. And at this point, we're ready for a balancing of charge. Now, when we go to balance charge here, we have to do an evaluation of the total charge. So let me back up a second here, because this is really where people make mistakes. And this is one where we got lots of charges, so this is easier to see or better to practice in a more complex situation. Now, remember, hydrogen is a +1, and there's 8 of them. That gives us a +8 for all of our hydrogens. We have 1 MnO4, and it's a charge of -1. So our grand total here is 7. Over on the product side, well, that's a +2 because we've got one Mn2+. And waters are 0. We got 4 of them. Well, 4 zeros is still 0. So this side is a +2. So when we go to balance this for charge, we need to recognize we've got to bring that positive 7 down to that positive 2. Well, that would mean add 5 electrons to the left. So remember, you add the difference to the more positive side. So we're going to put 5 electrons on the left. And now we're balanced for charge. Now at this point, we're ready to look at balancing the electron transfer. Now the top reaction made 1 electron. The bottom reaction needed 5. So to balance this transfer, what we really need to do is multiply the top reaction by 5. Because if that reaction happens 5 times, we get the 5 electrons we need for the bottom reaction to happen. So that means we need 5 Fe2 pluses, making 5 Fe3 pluses to get our 5 electrons. Now we've got electron transfer balanced. Now we can add the two together and cancel. Now when I add these two together, notice my electrons on either side cancel. And at that point, I don't really have anything else that's common to either side. So that's going to be my balanced redox reaction. So since the electrons were the only things that were equal on each side, or that are on both sides at all, it's going to cancel to that. So that would be our balanced redox reaction. Now, this is actually for an acidic environment, and the clue is we see the 8H pluses there. So if the question asks us to balance this reaction in a basic environment, we're not quite done. We have a little bit more work to do. It's just not much work. So if a reaction occurs in a basic solution, you can balance it from your answer to the acid reaction. So rather than look at how you do this in each individual step, it's easier to just balance it for an acid reaction, just like you always do. And then at that point, once we have our overall balanced acidic reaction, you're going to add OH minuses to cancel out those H pluses. And that's going to give us our basic reaction. It's pretty easy once you see it done. So if you end up adding OH minuses to the side that had H pluses, remember H plus and OH minus give us water. So we end up producing water, and that may have to cancel out. But it's still a fairly simple process. So we're going to take our answer from the last problem, which is this reaction for an acidic environment. How's it going to change if we have a basic environment? Well, we have 8 H pluses we need to cancel out, so we're going to add 8 OH minuses to both sides. Now what that's going to do is turn our H pluses into water, and on the other side, now we're going to have 8 OH minuses. So we've now taken care of our acid, and now it's a reaction taking place in a basic environment. Now, one of the things you need to do at this point is cancel things from both sides, or partially cancel. We've got 8 waters on the left and 4 on the right, so that's going to cancel to 4 on the left. And everything else is as is perfect. So that would be that reaction balanced for a basic environment. And really, out of all the stuff we talked about, this is pretty much the only thing new other than the idea of oxidizing agent and reducing agent. So that ends our first set of notes for chapter 20.